All right, let's take a look at a couple experiments involving polar versus nonpolar molecules. In order to do this, we need to focus on a couple quick definitions. These definitions centers on what happens when a covalent bond forms. Now, we know that a covalent bond forms when two atoms decide that they want to share electrons and form a covalent bond. Classic example that we're used to in our everyday life is we know that hydrogen and oxygen will often get together to share electrons and form covalent bonds. What we don't often think about is something that we're actually pretty familiar with in our everyday life. We know, and from our own bitter experience, that there's sharing and then there's sharing. How I like to think of it is, have you ever seen two kids play together? Well, if you have, let's say, a couple 5-year-olds playing together, and they're passing a ball back and forth, they're going to share the ball equally. Two 5-year-olds playing ball, they're each going to wind up with the ball 50% of the time. But what happens if that 5-year-old is told to play ball with his 1-year-old little sister? How well do you think that's going to work? Who's going to have the ball most of the time? The 5-year-old, right? When is the only time the 1-year-old is going to see that basketball? When mom sticks her head out of the window and says, give the little ball to your sister, right? Share with your sister. So even though they're sharing the ball, we know that the 5-year-old would probably have the ball 90% of the time and the 1-year-old only 10% of the time. Now, technically they're sharing the ball, but the 5-year-old is definitely getting more than its share of the ball. The same happens for the electrons in a covalent bond. Well, in theory, oxygen and hydrogen are sharing the electrons in this bond. The oxygen's the 5-year-old, and the hydrogen's really the 1-year-old. Meaning that the oxygen is getting the electrons in this bond a lot more than the hydrogen is. That means that part of the time, the oxygen here has extra electrons. And if it has extra electrons part of the time, that means it develops a partial negative charge. Conversely, if the hydrogen is deprived of the electrons in the bond by its obnoxious older brother, that means it's going to be short of electrons part of the time, and it's going to develop a partial positive charge. Another way to think about it is, our oxygen and our hydrogen are sharing electrons. Those electrons have to pass between the hydrogen and the oxygen. We've all played with Hot Wheel racetracks when we were little kids, where they had the big swoop around one end and a little narrow swoop around the other. Actually, I never had these as a kid. You know what I'm talking about? Whoa! Right? We can think of that as the racetrack around oxygen and hydrogen. If electrons are traveling around oxygen and hydrogen, they're going to pass through the hydrogen side of the racetrack really quickly. They're not going to spend a lot of time around hydrogen, but they're going to spend a whole lot of time traveling around the oxygen, meaning that part of the time oxygen has an extra electron, and part of the time hydrogen is short an electron, meaning that the oxygen develops a partial negative charge and the hydrogen develops a partial positive charge. In chemistry, we denote a partial charge using the Greek letter sigma, and it looks like a European baby face. Wah, wah, wah. Speaking of babies in comic books, let's go with Aqualad. Go with Aqualad. Everybody write down Aqualad. All right, once you've taken care of that. So when we have hydrogen and oxygen forming a bond, they're not sharing their electrons equally. When two atoms share the electrons in a bond unequally, the result is a polar covalent bond. And in this polar covalent bond, you're always going to have an atom that has a partial positive charge and an atom that develops a partial negative charge. Matter of fact, this is really kind of part of the definition of a polar bond. This results in one atom developing a partial positive charge and the other developing a partial negative charge. When we look at these bonds in the context of a larger molecule, it can have serious ramifications. Because molecules are made up of lots of atoms bonded to lots of other atoms. Not only that, but they have a three-dimensional shape to them. The water molecule, our favorite molecule, exists in what's known as a bent shape. Think of water as looking like a boomerang. One of the best TV networks ever, by the way, especially in the morning where they still show the original Teen Titans cartoon. It looks like a bent boomerang. And what happens is, you have these hydrogens with partial positive charge and the oxygen with a partial negative charge, resulting from the two covalent bonds at play here. When we look at partial positive and partial negative charges in the context of molecules, we like to sort of add up the direction the electrons are going. And when we do that, when we look at water, what we can see is we can see that water has two distinct areas. It has an area down here where we have a partial positive charge, and it has another area up here where we have a partial negative charge. Because this molecule has two areas, one with a partial negative charge and one with a partial positive charge, we refer to water as a polar molecule, because it has two poles, right? A negative pole and a positive pole. We also can refer to water as a dipole, or a molecule that has two poles. Everyone do me a favor and write down Lagoon Boy. I hope everybody writes down Lagoon Boy. So water is an example of a polar molecule. Now we said there were two scenarios for the kids playing with the ball. Some that played nicely with the ball together and some that didn't. Let's take a quick look at some kids playing nicely with a ball. While oxygen and hydrogen may not be able to share equally, carbon and hydrogen love to share equally. Carbon and hydrogen would be an example of two five-year-olds playing together. That means they're going to share these electrons equally. And if they share equally, the distribution of electrons is going to be equal, and no poles will result. No partial negative or no partial positive or partial negative situations will exist when the electrons are shared equally. We refer to this equal sharing of electrons as a non-polar covalent bond. Ask ourselves, let me also elaborate just a little bit. Molecules in which all the electrons are shared equally, such as hydrocarbons, or such as I shouldn't say hydrocarbons, such as molecules that consist of only carbon and hydrogen, are referred to as non-polar molecules. Okay, so we have nonpolar molecules and we have polar molecules. How do we know when we have what? And why do we care? Why should Aqualad, who you're writing down, going to care about this particular thing? Well, first of all, how can we estimate Well, this is actually a very, very complex question. How do we know when we have polar or nonpolar molecules or bonds? We could spend days talking about this, and we could go into great details about molecular shape. Right now, and I may even go into this in more detail later on in different parts of the course, but right now we're going to follow the KISS principle here and keep it simple. And we're going to say that we have a nonpolar molecule or a nonpolar bond whenever we have carbon and hydrogen bonded together or an element bonded to itself. We're going to say that we have a polar molecule in all other cases. Now, there are some obvious exceptions. One obvious exception would be carbon dioxide. Carbon dioxide is nonpolar. The reason it's nonpolar is because of its shape. Carbon dioxide exists as what's known as a linear molecule. It has a linear shape. The carbon, the oxygen are all right there in a line, just like that. What does this shape have to do with the fact that carbon dioxide is nonpolar? Well, oxygen and carbon are much different ages. They actually don't play nicely with each other. The oxygen wants to hog the electrons in the carbon-oxygen bond. But what happens is you have two oxygens bonded to the carbon, each wanting to hog the electrons in the different bonds. What you have is you have one oxygen over here pulling the electrons towards it. You have another oxygen over here pulling carbon's electrons towards it. So you have two oxygen atoms pulling with equal force the electrons away from the carbon. So what results is a tug of war for the carbon's electrons, where you have two equal forces pulling. And just like a tug of war where you have two people of equal strength pulling, the flag's not going anywhere. So because those oxygens are pulling in opposite directions with equal force, the electrons in the carbon wind up not going anywhere. You wind up with an equal sharing in a nonpolar molecule. So carbon dioxide is a notable exception to those guidelines I just gave you. And you're saying, Dr. Kelly, you just gave us guidelines and now you're violating it. Yeah, because I got distracted by myself. Because I was thinking about how much of a worthless member of the Avengers Stingray was. Everybody should write down Stingray. Everybody should write down Stingray. Why do we care about whether or not molecules are polar or nonpolar? The reason we care is because like dissolves like. Nonpolar substances can only dissolve or mix with other nonpolar substances. The opposite's also true. Polar substances can only dissolve or mix with other polar substances. Nonpolar substances can only dissolve or mix with other nonpolar substances. Hence the fact that, ba-dum-ba-bum, drum roll, please. Oil and water don't mix. Why? Because oil is a nonpolar substance and water is a polar substance. Let's explore this on even a more deeply level. Inside a glass of water that you're drinking, the water molecules are interacting with each other. And they're interacting through each other with those various charges. The partial positive charge on one oxygen is attracting the partial positive charge on the hydrogens of another water molecule. And what you have is you have all these associations and bonding going between the different ends of the different water molecules. This force of attraction between the water molecules is known as a hydrogen bond. And in order for another molecule to dissolve in water, it has to be capable of interacting with those polar ends of the water molecule. For example, we're all painfully aware of, I'm sure, of the fact that ethanol or alcohol dissolves in water. Ethanol, drinking alcohol, has a partial positive charge on its hydrogen and a partial negative charge on its oxygen, allowing it to interact with the water molecules via hydrogen bonding as well. So in order for two substances to dissolve, they have to have a way of interacting. Well, oil, poor old oil, is just carbon and hydrogen. No partial positive or partial negative charges. Therefore, it has no way of interacting with the water. It can only interact with other molecules that are boring like itself and have no poles. A matter of fact, what happens when you add little drops of oil into water? You see those little blobs of oil, right? As the oil circles up, so to speak, to try to minimize its exposure to water. We said that carbon dioxide is nonpolar and water is polar. So carbon dioxide in our soda has no way of interacting with its water. So what happens? Well, all those carbon dioxide molecules that are in our soda cluster together. It's almost like they're grouping together for protection. Or it's like another way to think of it is boys at a middle school dance, right? They're scared to go talk to the girls, so they all cluster up to minimize their exposure to the girls they're scared to talk to. That's why we see these bubbles of oil or carbon dioxide form in water. They don't have a way of interacting with the water. So they're clustering together to exclude the water. And the water's excluding them is another way to think about it. If they'd only talk to each other. If only they'd listen to a good king like Aquaman. Why doesn't everybody write down Aquaman? If you can't fathom who Aquaman is, you should also write down fathom. Perhaps one of the, right up there was Spawn and The Walking Dead, and Invincible as a best-selling indie comic. Fathom. So you should be writing down Fathom and Aquaman. Experiment. You're going to be making a lava lamp, and you're going to make that lava lamp by manipulating the fact that oil and water don't mix. A fancy way of saying two things don't mix is the word immiscible. Won't mix in any amount, oil and water. The opposite of immiscible is miscible, which means the two substances will mix in any and all amounts, such as alcohol and water, right? We know that you have some alcoholic beverages where it's 1 to 2% alcohol and 98% water. Then you have other alcoholic beverages that are the opposite, right? It's 90% alcohol and 10% water. So you have miscible and immiscible. I think that's what we're going to take it from here. And that's it for this lecture. Beep.